I designed this to be destroyed. This is the third video in the lightning series, but now it's getting us back to the actual boat project. Theory was needed to explain why I had to create this, and I needed to learn the theory about lightning to know how to design this. So what is this? So for reasons I'm going to explain in this video, but I don't like burying the lead, it is impossible to save anything on the masthead during a lightning strike. The best thing you can do, and what this board is designed to provide for me, once it's assembled and programmed, is a sacrificial node. On most sailboats, you have a whole bunch of wires that go up the mast. You have your VHF coaxial wire, you have cables for your steaming light, for your anchor light, for your tricolors, you have your wind instruments, and if you're the kind of person that likes TV, you might even have a TV antenna up there. You might have a 5G repeater. Whatever the case is, depending on how you've set up your boat, you have a whole bunch of wires going up the mast. Every single one of those is a path for the current from a lightning strike to travel down the mast and through the rest of your boat and destroying everything in your boat. Until very recently, that's what I was planning to do. In fact, I've got my mast currently sitting at Clacko Spires in Oakville, and when I dropped it off, I told them that I wanted a second conduit in. I had all of this stuff planned. I knew how I was going to wire. In fact, when Gert was visiting last year, another one of my friends, Andrew, and him helped me pull the new coaxial line, the new wires. That's how confident I was in how I was going to set up the mast. And I told all of this to Clacko. And then I sat down and I kept learning about lightning, and I realized, nope, I have to scrap all of that and start over. Understanding that you cannot save anything on the mast during a lightning strike, your next best option is to create a firewall. And that is, in part, the capacitor bridge I've hinted at in the last couple of videos. But more, what it really comes down to is minimizing the different paths that come down and interface at all with the rest of the electronics on your boat. And for those interfaces to be as skookum as possible so that during a lightning strike, on one side, you divert as much of the current away from the wire as possible, and on the other side, the amount of current that does go down those wires is hopefully low enough that your mitigation strategies at the base means that it doesn't escape the mast into the rest of your boat. It's a sacrificial node, not to be confused with a sacrificial anode. So the fundamental purpose of this board is it's going to have an ESP32, a terminal block for an NMEA 2000, and 6 lighting circuits. Each lighting circuit is a dedicated LED driver with redundancy, for reasons I'm going to get into in a bit. Now, before I go into more of this, let's do a little bit more lightning theory, because that explains why this is so important. I talked about it in the past how, at the moment of contact, where the streamer rises up and makes connection with the stepped leader, you have a nearly instantaneous dump of 30 kiloamps onto the air terminal. 30 kiloamps being the IEC 62305 standard negative cloud to ground strike. It's the median strike. It can be higher, it can be lower. Because the impedance between the tip of the air terminal and the grounding plates is roughly 15 microhenries. It's probably closer to 17, but we're using 15 for easier numbers. That results in a voltage increase of about 450,000 volts because the current dumps in a span of about 1 microsecond, 1/1,000,000th of a second. So I've been going with that number for a while, but what changed since the last video and this video is I was trying to understand how is it possible to dump 30 kiloamps in 1/1,000,000th of a second? It didn't make sense to me because I understood that the plasma channel connecting to the cloud was effectively a low resistance wire. But still, it covered kilometers of distance. It should take time for the charge to drain out the cloud, down the lightning bolt's path, the plasma channel, and into the boat. It just didn't make sense. So this led me down a path of understanding the actual mechanics, the physics behind how a lightning bolt forms, propagates, and dumps its current into the water. I say water because we're all boats here. Basically the same on the ground, but ground people have it so much easier, I'm just not even thinking about them. Sorry, ham people. So inside the cloud, inside the cumulonimbus, in that central region where you have the large body of negative charge, first thing to understand is that it's not a large globular single charge region. It's actually a whole bunch of pockets of charge. Those pockets of charge are kind of like bubbles. They could be near or far from each other, but you have this charge region. That becomes important when we start talking about secondary strokes. But for now, let's look at just one of the charge regions, the one that is going to be the initiator for the lightning strike that is going to hit the boat. Okay, so what's happening inside of this charge region, this charge bubble? So we talked before about how air has a dielectric strength. The laboratory number usually quoted is 30,000 volts per centimeter. However, we've also said that in the conditions where a storm is likely, on the surface where the boat is, it's closer to 5 to 10 kilovolts per centimeter because of the higher humidity and the salt aerosols in the air and whatnot. So inside the actual body of the cloud, where the charge regions live, the dielectric breakdown strength of air is around 10 to 20,000 volts per centimeter. Not too different from down on the boat. However, when they measure the strength of the electric field using balloons and aircraft flying through the clouds, badass, they measured that on average, it rarely gets above 1,000 to 4,000 kilovolts per centimeter. So in theory, there should never be any lightning because the negative electric fields inside there are well below the dielectric strength of the air. Yet, we have lightning. So what's going on? So if you recall from when we were talking about how the charge actually accumulates, you have the collision between ice crystals striking grapple being that big spongy hail, in the presence of supercooled liquid water. When that collision happens, depending on the temperature, you have a charge transfer. And then the ice crystal shoots up into the top of the cloud, and the grapple is left with a charge, with a negative charge, an excess electron. All of the grapple in the region, in that charge area, is carrying excessive electrons, building up this larger and larger negative electric field. You have these little floating blobs of water, these little droplets, that are floating in this charged area. They themselves are not charged, but they're influenced by the charge. And they're influenced in two ways. H2O is a dipole, as we talked about in the last video, and that alone makes it want to stretch apart. The negative wants to move away from the negative electric field because negative repels negative, and the positive wants to be attracted to it. So you have the surface tension of the water holding it into a ball shape, and you have the electric field trying to squeeze it. You also have dissolved impurities in the drop of water, and those impurities have a charge and react to the overall charge as well. So the charge carriers that are dissolved into the water, the negative are going to be pushed to one side and the positive are going to be pushed to another. There's a point where these forces overcome the surface tension and that little bubble of water suddenly flattens out. Well, it doesn't flatten out, it turns into a cone, something called a Taylor cone. This Taylor cone is, very cool name, a hydrometeor, and it's generated by the field effect. Is that right? Field enhancement. So this process that creates the Taylor cone is called the hydrometeor field enhancement. When you're dealing with this kind of stuff, the names are just flipping amazing. I love it. And the idea of a hydrometeorite is just, it's appropriate because of what happens next. And this is the initiator of a stroke. As it flattens out, recall when we were talking about the air terminal and we were talking about why blunt tips work better than pointed tips because the pointed tips send off their streamers too soon? Well, when you have the water droplet reshape into a Taylor cone, into this like cigar-shaped thing, it has a very fine pointed tip. And at that tip, the field enhancement is such that it starts to send off its own coronal discharge. It starts to strip neutral molecules of their electrons and accelerates them and shoots them off. Kind of like a really tiny railgun. Okay, so now we have the formation of the Taylor cone and the ejection of electrons caused by electrons being ripped off of neutral molecules in the atmosphere, near where all of this is happening. That electron shoots off and it strikes, usually an oxygen or a nitrogen, and knocks off an electron from that atom, creating a second free electron. Now, at the moment of collision, if you're thinking about this like a billiard ball on a pool table, you would think that the first ball or the first electron would strike the second electron, knock it free, and they both would slow down. and that does happen. However, because they're doing this inside of the electric field, as soon as they leave their host, they start to get accelerated. So over the mean free distance, the space between when the electron leaves its host and strikes the next point, it has room to accelerate. Again, kind of like a railgun. Now you have these two electrons flying off, and they're kind of pointed because of the direction of the original hydrometeor. It gives a bit of a bias to the direction. Those two electrons strike two more atoms, knocking off two more electrons, and now you have four free electrons, and they all get accelerated. So you have this cascading effect where 1 becomes 2, 2 becomes 4, 4 becomes 8, 8 becomes 16, and it keeps multiplying. And this is called an electron avalanche, also known as a Townsend discharge. And this starts to create a plasma channel. Now, this plasma channel is going to proceed for as long as the energy can exceed the dielectric breakdown strength of the air. So this process does lose energy as it grows in length. So as this process is streaming out, it's sucking some of the electrons out of the charge, feeding it forward, but it is still dropping in charge. And as it drops, there's a critical point where it drops below the dielectric strength of the air, and at that point, the discharge stops. Now a race begins. Now, back where this all started, a bunch of electrons have fled, creating the plasma channel, and that dropped the local electric field. But all of the other charge carriers nearby, they are suddenly like, hey, here's a lower energy state. We want to go here. And their charge will start to run down behind, but it's not an instant effect. It takes time. So if you have enough electrons coming down from other charge carriers and traveling down the plasma channel fast enough, what ends up happening is at the front of the plasma arc, you have a growing buildup of electric field as more and more electrons start to crowd into the end. If this doesn't happen fast enough, that plasma channel cools down and it stops being able to carry electrons, and it all just peters out. Those electrons at the front get picked up by oxygen and dissipate into the atmosphere, and you have a failed attempt at a lightning strike. If, however, the electrons can flow in fast enough and they can crowd at the end to a high enough degree, they rise back up above the dielectric strength of the air, and it starts again. You have another hydrometeor shooting out an electron, and you can actually have this happening in multiple directions at the same time, and they all fire off a new electron avalanche, a new Townsend discharge, and another step occurs until it hits that critical point where it stops, and the same thing happens. The electrons have to flow down fast enough to build up the charge at the end to start the next step, starting to see where stepped leader comes in. Now, as the steps grow, the current flowing through the stem of the arc, I said a moment ago about how you have a lot of different branches. Most of them die. But because of complete randomness in the atmosphere, some of them survive. So as the steps grow and grow and grow, they branch out, most die, a couple survive, you have growing current coming through the stem of the plasma discharge, through the leader. As these electrons flow, they're heating up the air. Once the plasma channel rises above 1500 degrees Kelvin, the plasma channel stops being a cold plasma channel and becomes a hot plasma channel. At this point, the air itself becomes a conductor, and it drops to be a very low resistance path forward. And now it makes it easier and easier for electrons to travel down the path to reach the stepped leaders, the ends of the different branches that are heading in random directions, but one of them is moving towards the ground. So step by step by step by step, the stepped leader is getting closer and closer to our boat. The key thing to understand is that every time the stepped leader halts and current has to flow in, you have this charge region that it's kind of like a really spicy sausage sitting just above your boat. It might be a meter to a few meters in diameter, and it might be several meters long, but in that relatively small area contains the full 30 kiloamps that's going to dump into our boat very shortly. So it gets closer and closer and closer to our boat. Our boat is sitting here, and it's got its air terminal that's rounded, so it's holding off until the step leader gets close, 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 and at just the right point, it sends up the streamer. That streamer connects with the stepped leader and finally closes the circuit all the way from the cloud down to your boat. But the key thing is the rise in current, that 1 microsecond we talked about earlier that translated into 450,000 or 510,000 volts if you're using 17 microhenries, which is closer to my real boat. At that point, in that 1/1,000,000th of a second, the voltage potential of the lightning rod spikes. Now, on my boat, the VHF antenna is sitting about 24 centimeters forward. The dielectric strength, as we said, is optimistically around 10,000 volts per centimeter. That translates to a gap of 240,000 volts. Anything over 240,000 volts is going to allow an arc to form from the lightning rod to my VHF antenna. So now I admit, I am not the best at math, but last time I checked, 450 and 510,000 is higher than 240,000, meaning that arc is going to form, and at the moment that that arc forms, current is going to start to flow into the antenna. Now, because it did have to jump the arc, it is going to be less current than it would have been had it been closer or had it been grounded at the masthead. I'm focusing just for a moment on the VHF antenna just to keep the active variables low. Now, my first reaction was, oh, well, I don't want that arc. Why don't I just bond it right at the masthead so that as the air terminal rises in voltage, so does the VHF antenna, and it blocks the arc from forming. That would work, but then it completely defeats the whole point of having isolation. Because I have a direct link right at the masthead, it means that far more current, because it's low impedance, can pass into the coax wire, spiking the voltage on the coax wire so high that there's nothing I can do to isolate that voltage to just that wire. It is going to hit the radio, and then through the radio to the 12-volt system, and there goes my electronics. I must keep the isolation between the VHF antenna and my weather station and my lights as far down as I possibly can so that I have the highest impedance between the masthead and the base of the wires where I'm going to have my firewall built. So we have an arc that forms and hits the VHF antenna. Simultaneously, my air terminal, and in my case I'm building it so that this is going to sit on top of my tricolor lights. I haven't designed it yet, but the lights will be sitting right here. This is going to be sitting about 40 centimeters back. It's not as guaranteed that it's going to strike this, but I'm operating under the assumption it would. In either case, I have an arc that goes to my VHF cable, and I have an arc that comes to my weather station / lights. When the arc forms to the weather station and the lights, their power cords are going to start carrying tens of thousands of volts as well. Okay, so every wire that's coming down the mast is a wire that I have to build a firewall for. And every firewall that exists is a firewall that can fail. So understanding that the primary goal in a lightning strike is to minimize the risk of damage to the rest of the equipment. Nothing I do is going to save the equipment on the masthead, so there's no reason even trying, and everything shifts towards a mitigation strategy. That mitigation strategy is to keep the voltage rise at the base of the mast, where it actually connects into the boat, as low as possible so that the firewall can do its job. I can do nothing about the VHF wire. It must come down and go all the way to the radio. For that, unboxing. I have a Polyphaser. It is the India Sierra Bravo 50 Lima November Charlie 0. Whoops, and that was the manual. This is the VHF's firewall. In that is a TVS diode and a gas discharge tube. I'm going to explain how those work in just a moment. The reason I'm setting that aside for a minute is because I want to talk to you about this, and the VHF doesn't go through this. What does go through this is a 24-volt power wire. Instead of having a whole bunch of wires going up the mast, I now have a single 14 gauge, 24 volts, actually 25 volts, wire powering this board. And from this board, everything else on the masthead is routed. So right now, the Airmar 200WX, which is my weather station, goes through NMEA 2000 wires to my NMEA 2000 bus. And then A project I haven't shown you guys yet is the Muirgun MFD that actually parses all of the NMEA 2000 data and turns it into a console. Again, that'll be in a later video. If I ran the NMEA 2000 cable from the AirMar 200WX down the mast and into the main backbone, which was the original plan, then it meant I would have had to create my own TVS diode plus gas discharge tube firewall for the NMEA 2000 bus. Could I have done it? Yes, I could have. Would it have caused problems? Probably not. But it's another point that something could go wrong, and the current from the lightning strike could arc over it into the rest of the system. If I can get rid of the firewall and turn it into an air gap, haha, that's better. And that's what this here is for. That's a terminal block that the NMEA 2000 wires are going to connect into, and this is the ESP32, which is going to read the PGN packets coming in off of the NMEA 2000, package them up in TCP/IP, and send them down over the wireless network. This is a Raspberry Pi 4 with a Copperhill NMEA 2000 and NMEA 0186, I think it is. Whatever it is, the NMEA 2000 is what I care about. It's a hat that allows me to read the data. This being a simple Raspberry Pi has a wireless interface and a wired Ethernet interface, which is what I'm using currently. So I've already learned how to tear up PGN packets and turn them into data that I can inject into my database. That makes it relatively trivial to then do the same thing on this board, turn it into a standard Ethernet stream, send it over the wireless air gap to the NMEA 2000, and have it listen to the CAN 0 bus, which is what it's using right now to read the physical NMEA 2000 bus, and also listen to a particular socket that this is going to be built to talk to, and drop the PGNs that way. And then the receiver, which is listening and parsing and storing the PGN data, it just has to listen to 2 points for PGN packets to arrive. Once they arrive, the processing is the same. So job 1 for this is to create an air gap for the NMEA 2000 device sitting on the masthead. One of the benefits of the AirMar 200WX is that it's my wind instrument, it's my barometer, where I would normally possibly, depending on modern equipment, have a few different devices on the masthead. It's one and does everything. So this gives me everything I need. The second job is lighting. ABYC says that if you're going to have digital switching, there has to be a mechanism for a manual override in case one of the lights gets stuck off or stuck on. I can't do that. If I try to do physical switches, I've defeated the whole point of making this thing an air gap device. So what I've created is, for every one of the 6 lights being controlled, and those lights are steaming light, anchor light, tricolor port, tricolor starboard, stern tricolor, and spreader lights for lighting up the deck. So I've got the 6 circuits, I've got the 6 circuits, and each one of them has 2 separate drivers. The circuit is designed using E-fuses that allow me to measure the current traveling through the E-fuse. I have created a bunch of aluminum PCB boards for mounting LED modules to. The actual LED modules I've chosen are the OSRAM, the AMS OSRAM LED modules. These are professional grade modules designed for use in things like traffic lights. They can get extremely bright, but that means I can run them at a fairly low percentage of their total rated output and run them much cooler and so more efficient. How they're going to actually be strung up, I'll deal with in another video when I actually build this. What matters is that I know when I turn a light circuit on, how many milliamps it should draw. If I turn on a light and the current doesn't match what I expect within certain tolerances, I can say, oh, that circuit has failed. Turn it off and turn on the backup. For each of my lights, whether it's the steaming light, whether it's the anchor light, whether it's the tricolor lights, there's actually going to be 2 independent rows of LEDs, each one controlled by an independent LED driver off this board. That is my answer to ABYC's requirement to have a mechanical backup switch. I have a totally separate second switch. Also, because I plan to be able to run my boat with the mast down, I am going to have on the boat a second independent stock that gets mounted on the coach roof. So even if this completely dies, I still have lighting. I still have my nav lights. I can still meet all of the requirements. I just put the stock up and voila, I'm back in business. So as you've probably already figured out, the benefit of putting all of the light controls under wireless control, they're all driven by the same ESP32, is I don't need to run any lights anymore. Now, When I designed my circuit breaker panel, I had thought at the time I was going to have breaker panels for all of them, and now I need a lot less circuit breakers, but that's a problem for another time. So there you go. That is why I designed this to be destroyed. This is the heart of the sacrificial node on the masthead. What this means is I now have 2 wires only coming down. I briefly hinted about how the Polyphaser has a TVS diode and a gas discharge tube, and that provides part of the firewalling capabilities. I'm doing the same thing with this. At the base of the mast, where the 14-gauge wire comes into the boat, it runs into one of these. Now, this isn't the exact model I'm using, but it is the same brand and same design. This is a mean-well isolated DC-DC converter. I am going to take the 12 volts coming in, step it up to 24 volts, 25 volts because it's tunable, and send it up the 14-gauge wire. The 25 volts that's going to enter this is high enough that I can run any one of my LED circuits in buck mode, just has to step the voltage down. It also means that I only have to send half the current up the mast, meaning I can use smaller wires. This has an isolation rating of 4,000 volts, meaning so long as the voltage coming in on the output side is less than 4,000 volts, this will act as a firewall and prevent any of the voltage from coming out the input side, feeding the rest of the boat. So my challenge then was to design a firewall system such that the output voltage stays below 4,000 volts. Okay. So we talked about how, because of the arc having to form, it increases the impedance, and the current is going to divide amongst all parallel paths based on the impedance. So the higher the impedance between the 2 paths, the less percentage of the current is going to go down that wire. So the voltage, if you recall, is determined by the inductance of the conductor between the source and the destination, times the current divided by how fast the current changed. So the lower the current is that jumps over to it, the lower the voltage rise. I can't control the rise time. I can't control the inductance, not directly. Trick on that in a second. But I can minimize how much current actually jumps onto that wire. Okay, it arcs over, it hits the wire, and it starts going down the wire. So my first tool in the firewall is a Fair-Rite choke. This is a Type 31 Fair-Rite choke. The power wires coming out of this go up, and before they go up the mast, they turn. This is not the right length of wire, and it's not the right choke, but it gives you the idea. At least 3 times. What does this do? As the current comes down the conductor, it's generating a magnetic field. That magnetic field interacts with the ferrite material and starts to create a counter magnetic field inside of this. So some of the current coming down the wire is converted into a magnetic field, consuming some of that current as it rises up. But what also happens, and how strong this effect is depends on how many turns you have, that magnetic field is in opposition to the flow of current, meaning not only is it burning up some of the current, turning it into a magnetic field, the magnetic field that is induced is fighting the flow of current. It slows it down. Remember that the voltage is, well, inductance, but that doesn't matter at the choke side of things. It is the change in current over the change in time. So by slowing down the rise time of the current, I am lowering the voltage on the other side. So there's step 1. Step 2 is taking the current. The current is rising on both the positive and negative conductor. The negative conductor is already tied to the lightning ground system and is going to directly discharge into the water. The positive side, though, does not. The positive side, under normal operation, has to be isolated. Otherwise, you have a short circuit. Electronics don't like working when there's a dead short. But in a lightning strike, we don't care about that anymore. So we have to find a way to, as quickly as possible and as stoutly as possible, connect the positive wire to the negative wire, because the negative wire is tied to the lightning's ground system. The first step in that is to use one of these babies. This is a TVS diode. This is a very big TVS diode. Now, the great thing about TVS diodes is that they can switch and close their circuit extremely fast. Extremely, extremely fast. However, they can't carry too much current, or they blow up. That's where this puppy comes in. This is a gas discharge tube. So don't let size fool you. the gas discharge tube can carry 40,000 amps. This, I can't remember what it is, but it's a much lower number, despite being physically bigger. Compared to most diodes, it can actually handle more power than you would expect, but it's still a pittance compared to the gas discharge tube. The problem with the gas discharge tube is it works through the same electron avalanche mechanism that started the whole lightning strike. Oh, hey, May. You gonna come up and say hi to YouTube? Oh. Kitty Interlude. Kitty, my dear. You're like, why are you holding me like this? You don't understand what camera is, do you? As the voltage starts to rise on the positive wire relative to the negative wire, this is going to start to clamp shut. And any voltage over its rating starts to be drawn through the TVS diode and bled out to ground. Generally, TVS diodes are used for static shock protection. And at the end of the day, what is a lightning strike but a massive static shock? This will take anything above its rating and clamp it to ground. And it happens extremely fast, as I mentioned. So, first, the current rise is slowed by going through the choke. It then goes down and it hits the diode. The diode rapidly clamps. It starts to conduct some of that current through the diode into the ground, further limiting the voltage rise. Remember, we're trying to stay under 4,000 volts. I would show you props, but I've now got a kitty on my lap, and she's can't interrupt her now, can I? Anyways, this here, though, it's not going to live for long. It's going to live for fractions of a second, like, I don't know, tens or hundreds of milliseconds. But it only needs to live long enough for the gas to start ionizing. Once the gas is ionized, it becomes a dead short. Inside of this gas discharge tube, we have a little mini lightning bolt. And remember that when the current flow raises the gas temperature above 1500 Kelvin, it becomes a low resistance conductor. This here shunts 40 kiloamps, which is more than the entire strike. And remember, it's not going to see the full strike current because the bulk of the current is going to go down the main mast. It's only a fraction that's coming down the wire. So this will easily be able to conduct the full current for however long the current rise lasts for. This is going to explode. This is a single-use item. But even though this only lives for a fraction of a second, because it turned on super fast, it bought me the time I needed for this to start conducting. Because we had an ability to shunt the current to ground from the almost very beginning, it means that the voltage on the input side here stays below 40,000 volts, meaning nothing gets out into the rest of the vessel. The polyphaser does the same thing for the VHF. The difference there is that it has the center conductor of the coax that carries the higher power, and its own internal TVS diode and gas discharge tube creates a short between that center conductor to the outer shield, and the outer shield is also tied to the lightning ground system. And that, ladies, gents, and fellow misbehaviors, is why I designed this to be destroyed. I'm the Digital Mermaid. I need to actually go build this now. Bye! Oh, and a side note, not this one, it's an empty one, but I started to assemble these. If you remember, I was working on these around Christmas time. All 4 designs are fatally flawed. I'm starting over. In fact, almost the majority of the time since the last video has been spent refactoring this. It's much better now.